So let us welcome Professor Bamba. So Professor Bamba, the stage is yours now. Please start.
Okay, thank you very much. Very kind introduction, and I am very happy to meet all of you. And in this presentation, I would like to talk about the inflationary cosmology and the transparency censorship conjecture. Outline of this presentation is as follows. In addition to the Planck 2018 results, the further constraints on the observations of the inflationary cosmology has recently been reported by the SCT telescope. And in this presentation, we consider two inflationary models and discuss the transparent censorship conjecture in these models. In the former part, we explore an extended version of the original natural inflation model with the double sign golden potential. In the latter part, we investigate the application of holographic principle to inflationary cosmology. Let me move to the first part. This is an extended natural inflation model with the double sign golden potential and the Planckian successive conjecture. The inflation is the essential mechanism to realize the homogeneity, isotropy, and spatial flatness of the current universe in modern cosmology. Inflation can also create the quantum fluctuations producing the large-scale structure of the universe. There are several inflationary models such as the R-square inflations proposed by Stravinsky, chaotic inflation, natural inflation, hybrid inflation, K inflation driven by a clinical term, Higgs inflation, and the inflation driven by the Galilean field. In this presentation, we concentrate on the natural inflation model. This is the two representative forms of the inflaton potential. In the left panel, we show the chaotic inflation type, the potential form. This is so-called the large field model. In this case, the tensor to scalar ratio is a little bit larger than the 0.01. However, on the other hand, for the natural inflation case, this is so-called.
Slides are not moving.
Excuse me, is this okay?
I think the slides are not moving.
Oh, really? No.
I think you haven't shared the entire screen. I think you have only shared the PPT
I'm
screen.
sorry. Okay, I
share
will
the
try
entire
to.
screen. Yeah.
Okay, I'm sorry. Can you show the slide? Okay.
Yeah.
Okay,
Yeah,
I
now
will
it is
try.
moving.
Okay, I will try to. What about? Is it okay?
Yeah, it is fine.
Yes.
Okay. I'm very sorry. So for the chaotic inflation, so the large field, this is so-called the large field model. In this case, the variation range of the scalar field during inflation is larger than Planck scale. So therefore, the tensor to scalar ratio is a little bit larger than the 0.1. However, for the natural inflation case, this is so-called the small field model. The tensor to scalar ratio is suppressed less than the 0.01. According to the Planck 2018 constraints, the spectral index of the scalar perturbation NS is around these values, and the tensor to scalar ratio, this is the upper bound, is less than 0.056. So this is a famous NSR diagram. The horizontal axis showed the NS, vertical axis showed R. We can see that for the Planck 2018 results, the R square inflations is favored, and natural inflation is out of the 2 sigma level. So from this figure, we can see that the small field models for inflation are preferred by the Planck result. Indeed, however, the Atacama Cosmology Telescope (ACT) observations is a little bit different from the Planck results. The NS is a little bit larger than the Planck result. So this is the same NSR diagram, we can see that the R square inflation is out of the 2 sigma level of the ACT observations. And the recent PRL paper there's proposed that such kind of a non-minimal coupling. This is the very smallest extensions of the conventional chaotic inflations. In this case, in the Einstein frame, in the potential, there are a little
Excuse
bit
me.
different
Still
from
it
the
is not moving. Professor Bamba.
Yes.
Excuse me.
Yes.
So still these tiles are not moving. We are there in the 5th slide.
Can you see?
Yeah. Now it came.
Okay, so I should not use the screen slideshow.
Yeah.
Okay, I will proceed this one. This is it okay?
Yeah.
Okay,
Yeah. Now
I'm
it
very
is moving.
sorry. So such a technical problem. So we can see that the non-minimal, if the non-minimal coupling is there in the chaotic inflationary type of inflationary models, we can see that in the Einstein frame, the potential form is a little bit different from the R square inflation type. So therefore, this kind of a model, we can fit the ACT data like this. Also, now currently the natural inflations is compared with the ACT observation, like such kind. And this is a very recent work. So in this presentations, we would like to consider the comparison of the theoretical model with the Planck result, not ACT. So that this is the inflationary models. The action is given by this kind of a form. The general relativity plus the conventional scalar field theory. However, we consider this scalar field is the pseudo-scalar field. For the conventional natural inflation, the potential is given by this kind of a form. We extend this kind of a natural inflation model to this two sign Gordon potential. We have 3 parameters, alpha, beta, and n. From now on, we use the parameter gamma combined beta over alpha. And we consider the homogeneous and isotropic universe as usual. In this case, the Friedman equations are given by these expressions, and the field equation of phi is given by these expressions. And the solar parameters are given by these expressions. And we define the number of efforts is given by this kind expressions. The subscript k and f refer to the Hubble horizon crossing time and the end of inflation, respectively. In this case, the number of effort is given by these calculations. So please see that these underlying parts. We can classify the several types according to the signature of these 3 forms, 3 parts. Later, I will explain these points. The spectral index of the scalar perturbation and tensor to scalar ratio are given by these expressions for ordinary Schroeder parameters, Schroeder inflations. This is the conditions of the end of inflation in terms of the Schroeder parameters. The horizontal axis shows the model parameter n. The vertical axis shows the Schroeder parameters. We can see that if the one of the Schroeder parameters is equal to unity, then the inflation will be n. Therefore, if n is smaller than this critical value, the epsilon is equal to 1, and then the inflation ends. However, on the opposite case, namely the n is larger than this point, this value, the absolute value of the eta is equal to unity, then the inflation ends. This figure shows the number of efforts as a function of the spectral index. The horizontal axis shows the NS, vertical axis shows the number of efforts. Please see for example, we can the blue region is the bicep Keck2 regions. The green regions is the Planck 2018 data. Blue region is a tighter than the Planck. So we can see that we have consistent model parameter regions with the Planck or the bicep and Keck results. And from these analysis, we find that the allowed range of the number of efforts of this model is given by this range. So from now on, we take the number of efforts is 55. We can consider the 5 cases that produce the NS and the value of the NS and R in agreement with the Planck 2018 data. So we have 5 cases. However, in this presentation, we concentrate on the case 4, this case. Basically, they're similar. The result is similar to the case 4, even for other 4 cases. So this is NSR diagram. The horizontal axis showed NS, vertical axis showed R. Please see, for example, the parameter N is equal to 0.1 or 0.11. This purple lines. So we can see that if the number of efforts 55, this model, it can be consistent with the observations. Also, this is R and NS figures as a function of the model parameter gamma. So on the left panel, we showed R. The right panel, we show NS. Please see this green line. We can see from the left panel that R is suppressed. R is smaller than the upper limit of the Planck result. We can on the right panel, we see that the NS can be consistent with the Planck result or bicep Keck result. Then we consider the reheating process following the inflation. The number of efforts during reheating is given by this expression. And then the reheating temperature is represented as this form. Finally, we can estimate this kind of the form of the reheating temperature. We can find the parameters consistent with the Planck 2018 data. For example, if the number of efforts is 55, the effective equilibrium state during reheating is this range. In this table, we show the range of the model parameter N and gamma consistent with the Planck 2018 data. The upper table, we show the range of N, this range. If we take the representative behavior of a reheating process, like such kind of, this is a kind of a similar to the dust-like. For example, W is exactly 0, then we obtain the reheating temperature order of the 10 to the 14 GV. This is a very high reheating temperature, namely the high scale of inflation. And we show the range of gamma, this type, this range. If we take the W is dust-like 0, then we also obtain the high reheating temperature. For other cases, we also have the parameter ranges compatible with the Planck 2018 data. And also, we consider the trans-Planckian censorship conjecture. We explain first the trans-Planckian problem. If inflation lasted more than enough, it's possible to observe the length scale which would be originated on the smaller scale than the Planck length. The trans-Planckian censorship conjecture, so-called the TCC, is as follows. The question how we should treat the trans-Planckian mode. This is the question that does not arise in a consistent quantum theory of gravity. In our case, the trans-Planckian censorship conjecture is given by these expressions. We relate this relation at these forms if we use the end of inflations when the floral parameter becomes unity. And we relate this constraint on our model parameters like this. And we find that there exist parameter values for which the TCC can be satisfied. For example, these values case. One more point, we would like to consider the swampland conjecture. This is recently, also in recent years, swampland conjecture has been discussed. It's argued that the Dositta space-time is difficult to be compatible with a consistent quantum theory of gravity. This swampland conjecture is given by these inequalities. Excuse me. For the present model, the swampland conditions cannot be satisfied because the solar parameters are much smaller than unity. Namely, the inflationary stage that we obtained very close to the Dositta-like inflations. However, indeed, we can say that it still deserves to be studied at the classical level and more precisely because a model with the Dositta solution is regarded as a consistent low-energy effective theory. Okay, let me summarize the first part. According to the Planck 2018 result, as a promising inflation model, natural inflation with the pseudo-Goldstone boson potential is considered to be the next candidate to R-square, namely the Sturm-Lewis inflation. However, I already indicate that the different results are suggested by the ACT. That we have, in this presentation, we have explored an extended version of the original natural inflation model with double sign Gordon potential. We have demonstrated that in the extended natural inflation model, the spectral index of the scalar perturbation NS and the tensor to scalar ratio R can be consistent with the Planck 2018 and the bicep 2 Keck observations by showing the NSR diagram explicitly. We have also discussed the realization of the rating stage with the rating temperature around 10 to the 14 ZeB and the trans-Planckian censorship conjecture for the present inflation model has also been argued. Okay, next, let me move to the latter part. In the latter part, I would like to talk about our second work, the holographic dark energy for inflationary cosmology and the verifications of the trans-Planckian censorship conjecture. According to the observations of type 1a supernovae, the current expansion of the universe is accelerating. It is so-called the dark energy problem. The universe is considered to be spatially flat, and then we have two main approaches. First is to introduce dark energy in general relativity. The second is to extend the gravity theories from general relativity at cosmological scales. The candidates of the dark energy and the modified gravity theories are as follows. First, the candidate of dark energy is the so-called the cosmological constant, the quintessence, and the fluid descriptions, and the holographic dark energy. In this presentation, the latter part, we concentrate on the holographic dark energy. The holographic principle is as follows. Entropy of the system is measured by area and not volume. Second, the candidates of the modified gravity theories are as follows, such as the F over gravity, and the DGP Bramwell scenario, Galilean gravity, Horndeski theory, and the degenerate higher order scale theory, massive gravity, and biometric gravity, and so on. In this slide, we would like to explain the relation between the holographic entropy and dark energy. It is known that the generalization of the black hole entropy is given by this kind of a form. If this parameter delta is exactly unity, this is the conventional Bekenstein-Hawking entropy. And here, the lambda is the cutoff scale of the small scale, namely the UV cutoff. And high energy regime, this kind of inequality has been proposed between the cutoff scale, small UV cutoff, and the entropy. We apply to the entropy of the cosmic horizon. And we also use this kind of inequality to the dark energy. In this case, we have this kind of inequality. By combining these constellations, we finally obtain the dark energy density given by this kind of expression. If delta is 2, then this is a cosmological constant. We explained the holographic dark energy. The dark energy density is given by this form. And we again consider the conventional and the ordinary homogeneous and isotropic universe. And we take the future event horizon like this. In this case, the holographic dark energy is given by this kind of a form. And in a homogeneous and isotropic universe, the Friedman equations are given by these expressions, and the energy conservations are given by these expressions, as usual. And the density parameters are given by these representations. And since we take the future event horizon by using the Friedman equations, we have this integral equations. And by this equation, we finally obtain the differential equation of the cosmic evolution of dark energy like this. The conservation of the dark energy is given by these expressions. From these expressions, we have this form of this kind of a form of equation. And equation state of dark energy is given by this form, and the deceleration parameter Q is defined by this and given by these representations. In this slide, we show the evolution of the cosmological parameters. The horizontal axis shows the redshift z. The vertical axis shows the cosmological parameters. The first is the density parameter, second is the equation state, the third is the deceleration parameter. Here, z is equal to 0 is the current time. So we can see that in the past, the matter is dominated. However, and some time close to the present time, the dark energy density dominated, and then now currently the dark energy is dominant in this case. And the third one, please see the deceleration parameter. We can see that around the present time, the Q becomes negative. Then this means that the current universe is accelerating. In the next slide, we show the equation state of dark energy. The horizontal axis shows the redshift z. This is the model parameter delta. Is we take some model parameters. If delta is unity, this is a Bekenstein-Hawking entropy case. So we can see that this line is the cosmological constant case. in some case, the crossing of phantom device can be realized. And the important point is that being independently of the model parameters, we obtain that W is less than -1/3. This means that the current universe is accelerating in this model. We can also show the cosmological constraints on the cosmological parameters like this, that the 1 sigma, 2 sigma, 3 sigma level, and we used the supernovae and the Hubble parameters data. This is a MCMC analysis. And we also consider the stability analysis by using the squared sound speed. This case, we obtain the sound speed, the squared sound speed is given by this form. If delta is equal or less than unity, then the squared sound speed can be positive. This means that this model is stable against perturbations. So let me move to the application to the inflationary cosmology of such kind of a holographic dark energy. The energy density of the dark energy is given by this kind of a form. Here, we take the infrared cutoff given by this kind of a form. The important point is that this form consists of the Hubble and the time derivative of the Hubble. And the Friedmann equation is given by this form. The time derivative of the Hubble parameter leads to this form and these equations. Taking integration in terms of the H, in terms of the number of efforts during inflation, where we obtain these equations. Here, capital C is given by this form. And from the expression of the H dot, we obtain the Sorrow parameter given by these expressions. And the inflationary observables, namely the spectral index of the scalar mode, NS, the tensor to scalar ratio, R, and the amplitude of the power spectrum of the scalar mode are given by these expressions. This is basically the same as the conventional Sorrow inflationary models. From these inflationary observables expressions, we obtain the capital C given by these expressions. Here, the capital C consists of the three model parameters, alpha, beta, and delta. And in this slide, we show the alpha beta space consistent with the Planck 2018 data. On the left panel, the horizontal axis showed alpha. The vertical axis showed beta. On the left panel, the model parameter delta is 0.1. Right panel, delta is 0.6. We can see that these are the consistent parameter range with the observations, 1 sigma, 2 sigma. And this is NSR diagram. The horizontal axis showed NS, vertical axis showed R. But this is a Planck observational 1 sigma, 2 sigma level. And we can see that we have some model predictions consistent with the Planck results. This is a table showing the values of the model parameters consistent with the Planck 2018 data. We showed the parameter alpha, beta, and capital C. Capital C consists of the alpha, beta, and delta. So basically, this table showed our representative model parameters consistent with the observations. We also show the correspondence between the holographic dark energy and the scalar field theories. First, the canonical scalar field case. In this case, this is very usual and conventional canonical scalar field theories. With the definition of the first order parameter, the scalar field is obtained by this kind of the integrations. And numerically, we can plot the form of the infraton potential. The potential of the canonical scalar field. Basically, since we consider the inflationary model, we can regard this canonical scalar field as an inflaton. So we see that the horizontal axis shows the scalar field, while the vertical axis shows the potential. We can see that this kind of a potential is classified to the large field potential. Next, we also consider the tachyonic field case. The tachyon field case is given by this kind of action, with the definition of the first order parameters and taking integration, the change of the scalar field during inflation is found by these representations. Similarly to the canonical scalar field case, we can plot the potential, inflaton potential numerically. Basically, even for the tachyonic field case, we obtain the similar behavior, namely the large field type, large field inflationary type. This is a basically similar feature of the canonical scalar field case, like this one. And also, again, we consider the Transpian censorship conjecture for this model. Since I have already explained the Transpian censorship conjecture and the Transpian problem, we just show the Transpian censorship conjecture form for this model. In this case, the TCC is given by this inequality. For the latter part of these presentations, this kind of censorship transparent gas censorship conjecture is rewritten to this inequality. We can see that by using the values of the present model consistent with the Planck 2018 data, so the left-hand side is order minus 14. However, the right-hand side is minus 54. So this means that this inequality cannot be satisfied for this model. However, we would like to mention that in the literature, there have been proposed possible solutions to consider to resolve the transparent gas censorship conjecture. The first is the greater part of the digital fluctuations are produced with the wavelengths roughly the Hubble horizon scale. The second is only the fluctuations with the wavelengths less than much less than the Hubble horizon are exponentially suppressed with kind of a exponential suppressing factor by some unknown mechanisms during inflations. Okay, let me summarize the second part. In the second part, we consider the holographic dark energy. Since the length scale is considered to be small enough during inflation, the energy density from the holographic principle can be expected to be large enough to drive inflations. Therefore, we have explored the application of the holographic principle to inflationary cosmology. The solar parameters, the scalar spectral index NS and the tensor to scalar ratio R have been analyzed by comparing with the Planck's and as our diagram parameter space for the constants of the present model has already been shown. Also, we have discussed that for the present model consistent with the 2018 data, the transplant consensus conjecture could not be satisfied. However, we have some possibility to resolve this problem. And we also finally slightly mentioned the related study. And recently the new form of the holographic entropy, the entropy of the black hole proposed by Barrow, this kind of a form. And this kind of in the literature recently, this kind of form is called Barrow entropy. This has already been applied to the black hole sum dynamics in these references, and applied to the cosmology and these references. And the first is professed by Sardakis. And also, in this case, the dark energy density, holographic dark energy, is given by this kind of a form. The point is that the delta is the parameters of the bioentropy. More from the Professor by the Professor Sardakis, also that this parameter is extended to a kind of a time evolution functions. There have already been written several cosmological works by Professor Sardakis for the case that the delta varies in time and the cosmological scale. Okay, let me stop my presentation. Okay, thank you very much.
Thank you, Professor Bamba. So it is now open for discussion. So let us start the questions or queries if you have. Participants, please unmute yourself and you can ask the questions to Professor Bamba.
Yes.
Yeah, Saintan, you can start. Saintan, you can unmute and ask your question.
Oh, yeah, sorry, sir. Actually, there is a net problem. Okay, thank you, Professor Bamba, for this amazing talk. So I had a couple of questions. The first one being that
Okay.
how does it resolve the Transplanckian conjecture to begin with? I mean, in a sense that what is the A initial you have taken? I mean, the Transplanckian conjecture was the relation between AIAF and Planck length should be less than 1 by HF, right?
Yes, like this one. Yes.
Yeah. So what is the AI you have taken?
What
AI
is the
initial?
AI? Sorry, excuse me.
Yes.
AI here.
Yes. Yes. Yes.
This is the initial. This is the scale factor of the initial time of the inflation.
Yeah, but in your model, when you are verifying that, how do you choose that your AI?
Okay. So basically, I understand your point. So this is sorry. For example, we can consider this kind of this is if it means that the scale factor at the end of inflation. That means that AF over AI is the how expanded the how large expanded during inflation. So this is kind of a, for example, exponential. This is exponential n, the number of efforts.
That I get it, but I am asking that in order to verify the Transplanckian conjecture, it
Yes.
seems like it is very much dependent on the choice of AI. I mean, the L of Pi is fixed, H of F and A of S is fixed when you are basically the slow roll parameters are going to 1 and you are probably fixing from there. But I am little bit concerned about how you are choosing the AI. AI seems like it's chosen somewhat arbitrarily. So in a sense that one can always satisfy the inequality by choosing arbitrary
Okay,
small AI.
understand. I understand.
Yes.
Yes, that's the important point because if the number of efforts is very, large, then that means that the inflation continues a little bit longer. So the longer should be okay because as longer is effective to solve the flatness problem and the flatness problem, inflation or monopole problem. However, if the inflation continue too longer, then even the smaller scale than the Planck length can be larger than the horizon, cosmological horizon. So that is exactly the problem of the Transplanckian problem. So your point is very important because if this so that in other words, that we can consider the we no we can not can we should consider the not so longer inflations. So that means that we should select the appropriate AI, or in other words, we should consider the appropriate number of efforts.
I see. So in your in the second paper where you have shown that this I mean AF by AI LPI into HF is less than some 10 to the power minus 56, etc.
Yeah,
So
yes,
what was in the second slide actually?
yes. This
Yeah,
one,
this one, this order of magnitude of 10 to the power
yes,
minus 10 or 10 to the power minus 54.
yes,
So what is
yes.
the choice for your AI here?
Ah, so this is basically the same. This is okay. This is the same as the Transplanckian censorship conjecture relations, and we take the values of the present model consistent with the Planck 2018 data. This model parameters for the our model. If we use these model parameters, then unfortunately, this inequality cannot be satisfied. That means that our model cannot satisfy this Transplanckian censorship conjecture relations.
Okay,
So
sir.
this,
Thank you. Oh,
yes, thank you. Thank
Okay,
you very
okay. I
much.
think I got it. Yeah, and maybe one small question that about typically the holographic dark energy. I mean, by the name itself, I mean it typically uses for the late time one, right? Because when you are taking the IR cutoff of a Hubble horizon, you are mostly interested in the late time, not the UV range of the field theory. So, how does it make sense to talk about the holographic dark energy, where the cutoff is from IR, to use it for inflation, where the cutoff is mostly like the UV theory, right?
Yes, that's a very important point. So basically, the holographic dark energy is explained to that and applied to to use to explain the late time cosmic accelerations, and then and one more the recently we can consider the okay. I just only showed. So this is a kind of a answer to your important point. Since the length scale is considered to be small enough during inflations, that the energy density from the holographic principle can be expected to be large enough to drive inflations. So this kind of a fluid description for inflations.
I see. Yeah, actually, I am little concerned in a sense that one side we are taking the Planck length to compare the Transplanckian one, and on the other length we are also saying that the energy length scale is large enough to use the IR cutoff. So that's why I
Yes.
got little confused. I mean, in a sense that
Yes, I'm sorry. So
yeah,
maybe
yeah.
my explanation is not so enough.
No, 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 that
And
is fine. I will definitely look up to it.
and,
Okay, thank you
and
very
also
much, Professor Bamba.
yeah, and also your point is very important. Although I explained this kind of presentation, but I'm also now thinking whether this kind of application should be better or not. So I'm also now still have been considering that this kind of scenario is effective or not. So maybe long, or maybe we have some more, we have to consider the more points to be consistent, to obtain the consistent scenario of the application of holographic dark energy to inflations, as you said. So that's the
Yes.
important point. Thank you very much. Thank you very much.
Thank you very much, Professor Bamba, and thank you for the talk. Okay.
Yeah. So Sally, you have some question? Yeah, please go
Hello,
ahead.
sir. Thank you so much, Bamba sir.
Yes,
It is really great to listen you here.
thank you very
Actually,
much.
I'm just clarifying the things. As sir mentioned that how we are
Sorry.
and he told at that time that the initial when the inflation start, it is there. You gave some range there. So we are, I guess, as I am understanding, we are taking or we are fixing the value of AI and
Excuse me. Maybe the first part you are now talking about.
Sally, can you keep your mic little closer because your voice is breaking?
okay, okay. Now it's
Now,
okay.
yeah,
Yes.
Actually, sir, I'm saying just to clarify, I am just asking this that the value of AI and AF, as sir mentioned. So, in the earlier slides, sir mentioned the range of E folding number, that the inflation starts for this E folding number and ends with this E folding
This
number.
one. Okay, this one.
Yeah. So maybe the value of AI and AF, we are deciding from that range now.
Uh, so you
Earlier
mean
one,
the
not this one, the previous one, I guess,
previous one?
where you mentioned the range of E folding number.
Yes, this one. No.
No, probably the contour plot where the Planck contour you have drawn, I think, is that
Yeah, where you mentioned the range of E folding number that for
after this
range
actually.
inflation stuff.
Mm, not this.
No, 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 no.
I think go back, yeah, after some. Yeah,
This one.
this one probably. Uh,
No, no, sir. Earlier one where you mentioned the range of E folding number for inflation. It is, in the starting
I
slide,
guess this.
it was. Yeah, yeah, this one, sir. This one, yeah, exactly. So
Yes.
here, yeah, here you are saying, you mentioned that 30, at 30, when the e-folding number is 30, then inflation
Yes.
starts, and at 55, it ends.
No, no, no. No, this is a kind of a number of folds is a kind of no, we can choose number of folds is not evolves. This is a we can select one number of folds. So in our model consistent with observations, we can take the number of folds during these ranges. So
Yes,
and
sir.
therefore
Yeah.
so not this number of efforts does not depend on the time, cosmic time. We can select the one number of efforts by taking some express some model parameters. For example, we can take the 55, or we can take of 50, or we can take of 45, something like that.
Yeah, but end range, like the end point of this range are mentioning for the starting of the inflation era and ending of the inflation era.
Ah, you mean okay. Number of efforts is not
I am saying this because a folding number is directly related to scale factor.
yes, exactly. However, okay, I understand what you mean. Okay, so number of efforts is given by this one, this form.
Yeah, yeah,
Okay?
direct. Yeah,
This means
exactly.
that
This is what I'm.
if we take the end of the inflation AF
Yes, sir.
or now the mm, scale factor out of the first horizon crossing time, then number of efforts is determined in one value, in one as one value, determined to one value. For example, 55 or 50 or 45. So in other words, we can take the value of the AK or AF, then we finally obtain the fixed number of efforts.
Okay.
Okay, can you understand what I mean? Number of efforts did not will not evolve because this is the integrated in terms of A.
Okay, sir. Okay.
Okay, thank you very much.
Thank you so much, sir.
Thank you very much.
Any more questions?